All right, here we go. This is class 15, packet 5. And we're going to stick with 1D conservation of momentum today. We'll get a little more complicated problems. Tomorrow we'll start into two-dimensional, and that's when conservation of momentum gets hard. Some of the hardest stuff we do second semester is two-dimensional collisions, and mainly because it's just so many numbers and tedious. But I'll try and limit that to just a few examples, and then we're going to move on because we got bigger fish to fry. Let's see here. Okay, oops. Okay. I did not do a dino hunt today. I wasn't looking for stamps. We'll double up tomorrow, but that's where you should be. And by the time tomorrow rolls around, I put this assignment up for you guys for the virtual kids. Tomorrow night at midnight, all of 5.5 has to be done. Okay, you should be up to 5.5.4. Tonight's assignment is 5.5.5. So you should be done with sheet 5. And that's going to get turned in tomorrow by midnight. It's 5% off a day. It's late, so try to get it in. And I don't know how many points I made it worth, for 30 or I think 30 or something. So it's worth quite a few points, about 6 points, 5 points a problem. And also 5.6.1. And so to keep up 5.6, we did the front of 5.6, but you got to now do 5.6.4. We'll get to that. This, of course, is still up there. This is for Thursday. The big payoff comes Thursday for you on the test, and it will be Thursday for you, just like it is for them, but it'll be Thursday. I'll email it to you by Thursday at 2 in the afternoon. We're not going to have a meeting on Thursday, so they'll get me from 1 to 2 to kind of get it ready to go for email. And you'll have the email at the latest by 2 o'clock Thursday. And then there's a quick turnaround time here. I need to have it back from you by midnight Thursday. Unless there's some reason why you can't work on it Thursday, let me know. If you turn it in on Friday, it'll give the usual 5% off, but I think I'll increase that unless you have a reason. Anyway, you only give yourself an hour, right? You give yourself an hour to take it. Okay.
Are we turning it into your porch?
You can. That's always an option. There's 3 ways to turn things in. 1, my box in my room. 2, the front porch. Or you can submit it. Now, I don't know if I put that submission on there yet. I'll add that assignment. So, and I know what you're thinking. I personally would rather you turn it into the porch, but I'm not requiring that. The only time I never require it, but I'd really like you to turn in your test B, like your test 5B on April 8th, whenever it is for you guys. That would be nice to be on the porch because I've got to be able to mark that up. This one I mark up too, but I guess I can print off, if you want to PDF it to me, got to PDF it, not take pictures. I cannot mark those up. They're all shadowy and messed up. So you got to PDF it to me by Thursday this week or Friday, either through email or I can make it so you can just submit it. But now on the submission for Canvas, the only format I'll accept is PDF. So I guess there's really 4 ways now to turn something in. Box in the classroom, box in the front porch, email it, or submit it through Canvas. What a mess it is. After May, we're done with this stuff. Hopefully we'll not have another pandemic in the fall and we'll all be back together. The fall, they're not accepting virtual. If you're going to do virtual in the fall, you're going to have to do it through Edgenuity. They're not going to have us teach virtual classes unless these variants take hold and we end up back in the problem again. So hopefully by fall, we're pretty much normal. And you all will be sitting in my AP physics class. We'll all be together. Okay. So we started off with this demonstration. and I turned it on. This is the air track, the linear air track. We spent a bunch of money on it back in 1999. The whole point to this was so that we could finally get good quantitative data, because before this, back in the 90s and the 80s, we would just slam stuff together and then try and get a ton. You could not. It was hopeless to get any good data because there's so much friction involved, and you couldn't get the timing right. So we spent the money. I'll show you this picture here. These are photo gates, and back in the late 90s, those were expensive. Now they're much less, or probably 1/5 the cost. And then these are very good timers. So in fact, those timers have been, that's a different timer. That's a more updated timer, but the timers we had then were real expensive. So we got these timers, we got this linear track, we got this vacuum system, all this stuff. It was around $5,000 for the grant. Now you could probably get the whole thing for $1,500, but anyway, so the whole point to this was this big expenditure over a period of 2 years was so we could finally get good data. And so I'll show you a video here in a minute of us trying to do that. So in class today, I just kind of turn it on and let them play with it for a while, so they get a feel for these are the wedges. That's Gold Wing, that's Red Dog, that's Blue Boy. Blue Boy and Gold Wing are the same mass, 88 grams each. Red Dog is 44 grams, so half the mass. You can make them so they'll link up together in an inelastic collision. And so you could put like Gold Wing and Blue Boy together. Then you got something that's 4 times the mass of Red Dog. And they slide back and forth on this linear track, which is kind of nice because it limits your math to one-dimensional. We'll do glance ball in the hallway. Well, I guess you won't, but I'll show you a video of it. It'll be the week after spring break. And that's 2-dimensional. So that becomes much more complicated. But this is one-dimensional collisions. And the idea was to have these wedges with the air track on, and it eliminates friction, was to have these wedges collide between the photo gates. So what would happen is the wedge comes in. I'll draw some arrows here. Blow this up. So the wedge comes in. Let's say it's Blue Boy. Blue Boy comes in this way. We then measure its velocity, and then here comes Red Dog. Okay, we measure its velocity, and we know the masses. And the reason, the way you register the velocity is there's a little cardboard. You'll see it on the video. A thin piece of cardboard that then breaks the plane of the photo gate. The way the photo gate works is it has a beam of light. And then when you break that beam of light, the timer starts. And when the beam of light comes back together, the timer ends. And so you'll have a delta X, which is the width of your cardboard. And then you have your time. So delta X divided by T, we have our velocity, which is fairly instant, almost pretty much instant. Close, because it's not little dx dt, but it's a small delta, so it's pretty close to being instantaneous velocity just before collision, and then they collide in here. They collide in the middle, and that was a bad color to choose. They collide here in the middle, and then they bounce back, and then so you have to have a finger on the timer, but you reset it real quick. We have people, that's their jobs. They reset it, and then they get the time on the way back out. We divide the width by the time, we have the velocity at the end. Then we have everything we need to prove conservation of momentum. That was in theory. Well, the problem is, and I show this thing, I bounce a ball. I have a golf ball, I drop it, and we talk about its initial energy, potential energy is mgh, right? Learned that in 7th grade. Potential gravitational energy is mgh, the weight of it times the height. And so it has a certain level, that golf ball. When it bounces, though, it bounces up to about here, which means you lose about 1/4 of your energy in the bounce itself. And that's considered a golf ball hitting the floor is considered elastic collision, right? We only have 2 choices. We got elastic or inelastic. Inelastic, it sticks. Inelastic, it bounces. So obviously it's elastic. But the thing is, to be a true elastic collision, this is the thing in physics, to be a true elastic collision, kinetic energy has to be conserved, which means that the kinetic energy at the beginning has to be the same as the kinetic energy at the end after the collision. Well, if that was the case, that golf ball would have risen to the same height at the end as it did, but it didn't. So it lost a fourth of its energy in the collision. Even a golf ball loses a fourth of its energy in the collision. Where does that energy go? It goes to noise. You hear the golf ball hit the floor, so that requires you to compress and refract air molecules. So that's energy, sound wave. It goes to the temporary deformation. Temporary is not permanent, but temporary deformation of the golf ball. And that video we saw the other day of the golf ball hitting a wall at a very high speed, that pancakes out and then reforms. It's not to that extent, but it flattens some. You're trying to flatten a golf ball with your hands, you can't do it. It takes a lot of energy. So it flattens that golf ball a little bit, just a little bit, then it rebounces and that sends it back up. But you lose a lot of heat in the molecules there. It generates heat. So the point is that even in elastic collision, it's not elastic that you could run numbers on it like a textbook version, like the fantasy version, right? In reality, when something collides, there really is no such thing as an elastic collision. Well, we realized that. This is always early in teaching. This is 1999, teaching physics anyway. I came from chemistry, right? I thought, well, it should work. So the bumpers, then there's little bumpers. If you look real close, there's bumpers on these things, little metallic bumpers. And the bumpers then would temporarily compress and then reform, and you'd hear the click. And we no matter what we did on the stupid thing, we couldn't get good data. We were still looking at a 30% error trying to run our numbers, and that's not acceptable even for high school. So the kids had an idea, and this is 2005, and I thought it was a good idea. I'll kind of let them run the show. And they took these, you can't see them very well, but there's some magnets. They took these computer magnets and taped them to the front of each wedge. They're light, so they can go in, they wouldn't affect the really flow of the thing. So the idea was the magnets would be the like charges, north pole, right? So they would rebound. That way they would come in, sense each other, rebound back, and we would get a collision, quote, collision, without any temporary deformation and with no noise energy lost. And so we should theoretically get good numbers. Okay, so I'm going to show you this video. Let me share a new screen with you. Okay, is it there? Yeah, it's there. Okay, so we share the screen. There it is. It's like a 10-second video here. This is of 2005. Okay. Let's move this. I can't see. Oh, okay. Okay. So here we go. We have the magnets attached to the front. We'll turn the air track on. See this little right here? There's that little cardboard slice that gives us our velocity just after collision. So you don't see them, but off camera there are 4 people that got their fingers ready to go on the timers. All right, here we go. We're still rolling. All right, so there's the timers. Here we go. They're going to collide right here in the middle. Okay, we'll show that again. So they did come in. They came together. All right, and they bounced off each other. Okay, so there's no temporary deformation. And we checked everybody. We had the right times. So we ran the numbers, and we had a 40% error. Like, all right, caramba. Oh man, all that money. It's when you reach that sick feeling that that we were trying to figure out why. Well, then, I mean, like I say, I was fairly new to teaching physics then, but then the realization occurred that we've introduced, anybody want to come up with the reason why it didn't work?
The friction.
There was no friction, right? I mean, it's an air track. There's no friction. These things glide back and forth all day long. Once you get a balance, they just sit there, and so there's no friction. What do you think? Turns out we introduced electromagnetics. We introduced the magnetic fields. When you bring in those magnets, that's great. They will repel, but now you have Maxwell's equations to deal with, which is a whole nother set of forces, which is physics 3, right? It's a third year of physics at Norman High, if we offer it. We didn't offer it this year because of COVID, but where they come in, bounce off, that's great. But now you got to bring in this magnetic fields. And so that at that point I said, okay, I give up. We cannot come up with. And so my task to them was find me a YouTube video of a quantified conservation of momentum experiment which proves conservation of momentum. And someone said, well, what if we went down to the electronic level, like electrons? Well, the problem there is it's electromagnetics. That's not just linear conservation of momentum. I don't know if you can find an experiment that does that, that quantifies it. I think we were chasing a ghost here, which, you know, it's fun to play with, but anyway. So it was a futile exercise, but you learn something. I mean, that happens in science all the time. They drop $10 million on something and nothing works. It just doesn't work. The theory was there. Well, how many trillions have we spent on the F-35? It doesn't work yet. I mean, you just keep throwing money at it, and we could keep throwing money at it. It's never going to work, I don't think. So I wanted to at least point that out, that we tried to do a experiment. I hate just telling you formulas, you know. So we try to do an experiment. Okay, back to this now. I think, well, maybe in college, but I don't think so. All right, so that takes us to this page. We did the front. We did all this yesterday. This is yesterday's work. We did this. Today, we're going to concentrate on the time we have left here, the next 30 minutes. We're going to look at the back. And so the back of 5-6, plot starts to thicken. This is homework. I made assign this for homework for him. Oh. Okay. Homework. So work on number 4 on your own. It's fairly straightforward. But let's work on today the 2 hardest problems as a class. 7 and 8 are the 2 most important problems on the sheet. They're the 2 that you'll probably most likely see on a test. So put a little TST by those. So let's first do 7 together. And then I'll send you to the board for 6, and then we'll come back and look at 8 at the end. Okay, so here we go with 7. I always made my protagonist, always made my villain in these Osama bin Laden, you know, back when we were all trying to, you know, after 9/11, everybody wanted to get his hide. So then we got him, and so then I trying to find somebody to replace him with, and so I was using Abu Bakr al-Baghdadi, and then I guess we've got him since then. So now I guess it's going to be, you know, the leader of North Korea or something. I got to find some kind of villain. So anyway, here's Joe Dynamo. Is on. The thing about this is, if you look at this problem, here's why these are, the math itself is not hard. It's the setup that's usually hard. So I strongly suggest you all go get yourself 2 colored pencils. You'll need the pen and a colored pencil for this one, and then you'll need 3 colors in number 8. So use a pencil and a colored pencil on this one. I'm going to make, so we have Joe Dynamo and then the wrench. Really, Baghdadi really doesn't play a role here. He's just the villain. But it's Joe and his wrench because, and we show pictures of this in classroom, but the ISS, right? You got the ISS orbiting up there, International Space Station. And if he's out there in a tether, as you see when these astronauts, and I posted this on Facebook, really good video of the astronauts out on the ISS yesterday or day before. This beautiful, oh man, you can see the Earth down below. It's just amazing. 4K or 8K video. But anyway, so Joe's out there doing some work, and then Baghdadi cuts the cable, cuts the tether, being a jerk. And so Joe is out there floating around in space. Well, how are you going to move in space? I mean, how are you going to get back to the ISS if you're sit there with nothing? You can't swim. You can't, do this and kind of get back because you're not like in water. You can't push up anything. You're stuck. If you got no jetpack or nothing, you're stuck. So he only has one choice, and that is recoil, right? He can throw something. He take off his utility belt. In this case, he throws a wrench. If you throw a wrench this way to the north, you'll move to the south. That's the other thing. And then someone said, in think of the second hour, they said, "Wait a minute, but what's the initial velocity? Aren't they all moving at a certain speed?" Yeah, they're the ISS, Joe, everyone's moving at 17,500 miles an hour. So isn't there already initial velocity? Yes and no. Yes, relative to the Earth, but relative to Joe and the ISS, there's no velocity. So your reference frame, you put a little dash curve around the ISS and Joe. And so there is no relative velocity in there between them. Okay, so it's going to be a recoil problem. I'll make Joe blue. Oh, sorry, blue, yeah. So this will be, I'm going to color code this. This is mass of Joe, MJ. What else? Quickly thinking Joe throws, so then I'll make the wrench green. Mass of the wrench is 1.2 kilograms. And the opposite of ISS, trying to get back. And he throws it with a speed of 8 meters per second. So that's relative to the wrench. So that is the velocity of the wrench. V wrench final. It's the final velocity of the wrench. Because remember, initially the wrench isn't moving. Joe and the wrench are zero velocity compared to the ISS to begin with. And then the next part is a different, that's a kinematic part. So we'll just mark it. We'll come back to it. I am buffering. Catch your breath here. Buffering. Okay, so this red part, we'll come back to it later. Once we get the con of mom worked out. Okay, now I'm going to do a drawing. So initially, and you can draw Joe and draw a wrench, but you're kind of, if you're an artist guy, it's fine, but kind of a waste of time physics wise until these things have actual dimensions. Once we deal with torque, then we have to have dimensions, but until then we don't. So I make Joe a dot, big dot. It's a big dot, little dot problem. I'm buffering again. All right, FedEx is here. Okay, here's Joe. And here's the green wrench. First off, they start off together. There's really nothing going on. Zero. So they're there and then they end up apart. So Joe is heading this way. The wrench is heading this way. Okay. We assume that the wrench is going to go a lot faster than Joe because what you lack in mass, you make up for in velocity. And so we have M, Joe, M wrench. And then we have, I only bring in new symbols when it's something new. So we have V Joe final, and that'll be question mark. I'm trying to find that. And then we have V wrench final. Okay, we know that. So here we go on the equation. You guys can stop me anytime. On the equation, then we start off with 0 because nothing's happening at first. And then we have, keep it in symbols first, mass of Joe. At the end times velocity of Joe final plus mass of the wrench times velocity of wrench final. Now, I don't want to isolate the variable like I normally do, like we said yesterday, is because I want to kind of keep in the whole thing a positive negative. Standard is to make to the right positive, to the left negative. So we'll go with standard. Occasionally it helps you not to do that, but we will make that. Well, actually, with free bodies, we'll show another way of doing it. But all right, so I guess it's time to plug in numbers. 0 equals 80 kilograms times VJ final plus 1.2, right? I'll keep it obviously MKS system. One doesn't do me any good to change it. 1.2 kilograms times 8 positive. It's going to the right. 8 meters per second. Dun, dun, dun. Okay, so the velocity of Joe then. Somebody punch that in. Pretty small. One point, yeah, just looking at this, take the 80 divided by, 8 divided by 80 is 0.1. So 0.12, right? Should be 0.12. I think 0.12 meters per second. Negative meters per second. But that doesn't answer the question. The question said, how long, let's assume he has a minute's worth of oxygen. Will he make it in time?
Wait, really quick, how did you get the VJF? How'd you get that number?
I multiplied the 1.2 times 8 and then divided by 80. So I isolated the variable. Yeah, so,
Okay, I see now.
yeah. So 8 divided by 80 is 0.1, and then 0.1 times 1.2 would be 0.12. So I've got to do the red equation now and then someone asked, well, how do you know it's not accelerating? I mean, why wouldn't you use the orange equations? Well, that's a great question. They get bonus for that. I ask them really good questions. And the thing is, to have an orange equation, you have to have some source of acceleration. You have to have some imbalanced force that's causing it to accelerate. And between Joe and the wrench, between Joe, really in this case it's Joe moving back to the ISS, there's no unbalanced force. And someone said, well, doesn't the ISS have mass? Wouldn't it kind of attract Joe? Yes, but that is beyond minuscule. That you'd be at 10 sig figs before you start to pick that up. You need to have really massive objects before a mass will start to accelerate things towards it. I would accelerate a wrench towards me in space, but it'd be really, really small because my mass is so small. And that comes from Newton's universal law of gravitation, which we will get to here in the next few weeks. Once we get to finally Newton's laws, which starts up after 2D collisions. All right, so the red equation then, we have delta x equals v times t. We're trying to solve for t. So delta x over v. Delta x, it told us, was 5 meters. So it's 5 meters away, 5.0 meters away, and the velocity is negative 0.12 meters per second. Uh-oh, doesn't that give us a negative time?
-5
There
meters.
you go. There's a quick stamp there, zoom stamp, catching that one quickly. Because Joe, back on our drawing, the ISS isn't in the drawing, but the ISS is back here, right? Here's the ISS. So Joe, so it's negative. So the delta x is negative. So we end up with about 40, I think that's about 44 or something like that. 44 seconds or something around there. And let's say if he had a minute's worth of oxygen, okay, he has enough time to get back, and then maybe 41 seconds. It's somewhere in there. Is it 44 or 41?
I get 41.6 repeating.
We'll go 42. So about 40, with our numbers, about 42 seconds. So if he had a minute's worth of oxygen, he'd still have 18 seconds left to do something once he gets back to the ISS. Okay. Now let's hold off on 8 for a second. Now we're going to do our going to the board problem, which means I'm going to turn the video off here in a second. I'm going to let you guys work number 6 on your own for a few minutes.
Mr. Askey,
Yeah.
did you know what equation to use?
On
Not the red equation, but the other one?
on this one, how did I know which one to use? Well, we have, let's go back here. We only have 4 choices. Like these are our 4 choices here. This is only, like this one, the one in yellow is if it's an elastic collision. 2 things hit and bounce off. And then the next one down below, that one is if 2 things hit and stick. So that's neither one of these cases. The next one is if something's not moving and then separates. That's called recoil, like a bullet out of a gun, or a wrench being thrown from a person. Like the person and the wrench start off together, and then they end up apart, right? Because he threw the wrench. So that's why we would use that equation. Sorry, this equation right here for recoil. Now, if he was moving relative to the ISS and then through the wrench, we would have to use this one. Okay. So those are the 4 scenarios this allows us to do these problems. Okay, so that's where I got that recoil equation. I'll mark that on there, recoil.
Okay, that makes sense. Thank you.
Okay, and then we just ready. Okay, so now we're back up here on this one. So that is, I mean, you're right. That is one of the first things you got to ask yourself. What of my 4 equations am I going to attack this one with? And by the way, remember, this is not on the test on Thursday. There's nothing about conservation of momentum. It's all projectile motion. It'll be on April 7th is when we test over this. So yeah, so I'll let you play with this. You got 1, 2, 3, 4 numbers to mess with. Get a good drawing, pick a color, and I'm going to leave you to it to attempt this as if it were a test problem or something. So I will hit pause. Okay, so we're back on air here. On the what I did was while they were working, I circled and labeled with blue being the big one, red being the small one. That's just my convention. But I labeled the numbers, units. Oh, look at the units. We got to make a choice whether it's CGS or MKS. I'm going to go CGS. You can do MKS, but I try and eliminate as many decimals as I can. So I'm going to go CGS system. That got me in trouble second hour because I was mixing up systems. They caught me. And then my drawing. On the drawing, you could put all your numbers in there. Sometimes we do, but I'm just putting in the symbols. So if there's a symbol in the drawing, it means that that is represented. So there is an M1, okay, there's a V1 naught, there's an M2. If it's a question mark, it's what I'm looking for. So without putting numbers in. Okay, there's no reason to repeat M1. I already established I know M1. All right, and this is I had kids at the board going, now, Mr. Askey, is this elastic or inelastic? Well, come on, man. I mean, if it's inelastic, the ball is going to stick to the club. When you think inelastic, think 2 lumps of clay. I mean, I know you're just trying to figure this stuff out, but that's when they stick together. So, and I think their point was that I had just made a big deal that there is no such thing as totally elastic collisions because there's always some temporary deformation. And that's true, but this is forcing us to put it into one kind of problem or another. You know, it's all black and white here. So it's got to be in this. The best approximation is elastic. Okay. So it's an elastic equation we're dealing with now. So color coded here. And I'll go ahead and put her down here. So we have M1 V1 naught plus M2. Well, V2 naught is 0. So let's just plus 0 because the ball isn't moving. It doesn't matter how big it isn't moving. Equals M1 V1 final plus, now the ball is moving, M2 V2 final. All right, so I'm not going to isolate the variable. I'm going to go ahead and just plug in numbers. Being careful, CGS, 110 grams times 6,500 centimeters per second equals 110 grams times 6,000. See, it drops to 60 meters per second, or 6,000 centimeters per second. Plus, now the golf is 46 grams times whatever it is, V2 final. Okay, so you plug in, I'll save you time, you plug in your numbers, and we get V2 final. Cannot come on, man. Getting tired. V2 final. I think Pepper, oh, kept me up again last night. They say dogs that get dementia, they sleep, we're reading articles on it, they sleep all day and they're up all night. So Pepper is deeply into dementia. So I'm like tired all the time now. So V2 final is 1197, right? 1194 centimeters per second.
Yeah, right around there.
Okay. Now, I had a student then in second hour that said, that seems awful. He's a golfer, right? So that seems really not like a very good drive. And so we said, okay, let's take a look. Let's compare this. And this is what you call back of the envelope. So we're saying, and you really ought to say that. You ought to, if it's ridiculously small, you ought to say, call me out on it. Come on. So let's compare that to Tiger Woods. Now, Tiger Woods can drive a ball 350 yards, all right? And so let's just round it off. Let's say it's not a great drive for Tiger, but let's say he drives the ball 300 yards. But we have an equation that we can use here. So let's say that 300 yards is his range, Well, I'm going to use delta x sub r equals v naught squared sine 2 theta all over g. And I wasn't planning on doing this, but then the kid asked, so I said, well, can we use physics to see if it's right? And sure enough, the range equation comes in handy. Let's keep it simple. This is BOE, which means back of the envelope, which means you're going to be rounding numbers right and left. You should be able to do it without a calculator. Okay. And so this is, let's say it's 45 degrees. Keep my number simple. 2 times 45 is 90. Sine of 90 is 1. And so it becomes delta x range then is v naught squared over g. So if I want to find v naught, it's the square root of g times delta x range. Okay, so now back to Tiger Woods, v naught then would be, let's keep it in feet per second. That's approximately 30. I'm keeping it back of the envelope. Feet per second squared. You're allowed to round off on this. Times 300. Well, 300 times, I need to get in feet, so that's 900. 900, sorry, not 9,000. 900. And so 30 times 900 is 27. What? Yeah, 27,000. So screw 27,000. Let's say I'm in a desert, have no calculator. Root of 27,000. Root of 25,000 is about 5, right? Sorry, root of 25,000 is not 5, but that's 500. V naught then, so a little over 500, 36,600, right? So we're looking at 5, let's say 550, that's feet per second. And how does that compare to 1100 to about 1200 centimeters per second? Okay, so multiply that to get it into meters per second. It's like pretty much like dividing by 3, pretty much, because meters is about 0.305 meters in a yard. So that's the same thing. This is back of the envelope, right? Back of the envelope. You shouldn't have to use a calculator. V naught then in terms of meters per second is about a third of that, which puts you at around, if that was, say that was rounded to 600, so it puts you around 200 meters per second, which is about, somewhere I messed up here, I think. No, I messed up here. Oh, no. Is that the square root? Hold it. Square root of 25,000 is what? Then that's 50. That's 500. Oh, okay. Daggone, I'm going to break my rule. That's where I messed up. Okay, the square root of, I need a calculator. 27,000 square root. Second square root of 27,000. Oh, okay. Not 550. That was messing me up. It's 160. It's about 160. All right, so then 160, a third of that's about 50. That's what I needed. That's about 50 meters a second. So 50 meters a second, that's about 5,000. That's 5,000 centimeters per second. Okay, so Tiger Woods hits the ball at about 5,000 centimeters per second, and compare our number about 1,200 centimeters per second. So we're in the ballpark. It's not crazy, but we're in the ballpark. So the number seems okay. Okay, well, ran out of time because I messed around with Tiger Woods, and we were going to do number 8, but we'll just go ahead and just do all of 8 tomorrow. No big deal. Okay, so your homework. Oh, the homework then is this. Tomorrow in class anyway, I'm checking for 5. You have to have all of 5.5 done. You'll have to have it all done tomorrow night to turn it in. And 5.6, you're responsible for 1 and 4 so far. 1 and 4. Okay. So far. Okay. Sorry I went over today. Daggone Tiger Woods. Mm.